Okay, good afternoon, everybody. Still some people joining. Okay, uh, we're going to start with our next topic, which is backtracking. So we have almost touched this concept of backtracking in our depth first search. So, as the word indicates, backtrack means just move back once from somewhere if you are not finding that path ideal for whatever purpose you had actually taken that path for. So when we you have that maze problem, you have to go from a start to a destination, and if you hit a dead end, we retract and we try the next available option, thinking it might take us to the end of our maze. So that is the whole concept of backtracking. We try all possibilities and we backtrack if we hit a dead end, or if we think that moving ahead will not make any sense, or it will not give us what we are looking for. Okay, so first we'll just go over backtracking and we'll see how we backtrack, how we uh, represent problems in a manner in which where we could, like, we can apply backtracking. Okay, so if you remember, when we did BFS or DFS, we create depth first or breadth first trees. So essentially, when we represent our problems in the form of trees, and then we perform a DFS or a BFS to look for solutions from that tree. So we'll be doing that, and then a couple of examples. There are more basic ones we do are sum of subsets, and we'll go over our knapsack problem. Then there is the eight queens problem, graph coloring problem. They all come under backtracking, so we'll be doing them also later on. Okay, so what is backtracking? You have many options available in front of you. Obviously, you cannot take all of them at the same time. You make a decision, you go towards one path, but then at one point maybe you realize this is not going to give me my desired goal, so I let me go back and try the second option. So you follow, like this, it's written as a methodical way of trying various sequencing sequences of decisions. So for example, the problem that we are going to take as an example is called the sum of subsets problem. So what you have in that problem, you have a set of numbers. We want to find out which, so how many subsets are possible here? 2 to the power 6, right? So how many subsets out of these 2 to the power 6, they sum up to 6. So if you just look at it, uh, by just looking at it, this is one subset that sums up to 6. 6 itself is one subset. You have 1 and 5, and that's it. I don't think any other combination is going to give you 6. So these are the three answers. So this is my solution, which I have just derived by visually looking at it. But when you have to write a program to do it, brute force would mean you get all the 2 to the power 6 subsets, and then you find the sum of all the elements in each one of them, and whichever is 6, you give that as an output. So obviously 2 to the power 6 is what, 32? Yeah, 32 or 64, whatever. So you cannot obviously waste time. In this case, it is an exponential number. The size is 6, 2 to the power 6. If the size is 10, 2 to the power 10. So it doesn't make sense to get the sum of all the subsets. There should be some other way. So what we do is we represent the problem in the form of a tree, and then we search the tree for the solutions. So let's first go back here. to our lecture notes. So I'll explain to you what the tree means. So another example, like I said, a maze, you want to go, you have many choices to make. You, let's say you start with the first choice available, which you think is the best. And that choice will lead obviously to more choices ahead. And then if you get stuck, you will come back and try your next option. Coloring a map is a problem. You're given four colors and you have to color a map with these four colors, making sure that no adjacent countries uh, they have the same color. So if you're making coloring an atlas, you have just four colors available. You have to color in such a way that no two adjacent countries have the same color. So that when we solve this problem, again it is done using backtracking. This will take it up later. So this is how we go. You start, you have many decisions to make. If you reach a dead end, you backtrack, come back, try the second option, backtrack, and maybe in the end you hit a success somewhere. Okay, so we we will see, we will represent our problems in the form of trees, and then we will traverse the trees, and then we'll see which path you take in the tree leads us to the solution. So in a tree, you have three different types of nodes. You have the root, you have the internal nodes, and you have the leaf nodes or the external nodes. So you can think of backtracking because your decisions are basically you have different options at any point of time to solve a problem or to get to a solution. So these different problems can be, the options can be thought of as uh, different children of, you are at the root and you have three paths. Let's say you're standing somewhere and you have three directions to go. So these are the three options available to you, so we represent them as edges. They will take you somewhere and from there you'll have more options available. So uh, we represent our problem in the form of a tree, and then we search the tree for possible solutions. Okay, our tree, you already know, you have a parent and you have children. Okay, we draw our trees in a top down fashion. So we are not using a tree data structure as such. We are just using a like a diagram for our choices, and then we are using our traversal algorithms to traverse this tree. And then so basically it's like you are creating all, virtually creating all the possible options, and then you are traversing them to see which one leads to you to a solution. We'll see why. So what is the general backtracking algorithm? If you are at node n, and if that is your goal, you're done. If n is a leaf node and it is not your goal that you're looking for, that means you have hit the end. You have no solution available, so you can return a failure. So for every node, you will explore every child of C. And if exploring gives you the goal you're looking for, you will return a success. Otherwise, you'll return a failure. Just a general. So what we are trying to do in a backtracking problem, it will be either we want to find a solution to a problem, just like your sum of subsets. There are only a few feasible solutions to that problem based on the values of the elements in the set. So, if there is no such thing, no such subset that sums up to something that is needed, you don't have a solution. But you can have another type of problem where we are not looking for one solution, we're looking for an optimal solution. Okay, for example, knapsack. So, we can use backtracking there as well. So, solution, that two versions you'll see, one where we are just trying to look for a feasible solution, and another where we are trying to find an optimal solution. So before going there, get back here to our whiteboard. Okay, so keeping this problem in mind, so what do we mean by representing our problem in the form of a tree? So brute force would be find all the subsets, get the sum, find the solution, end of story. But I want to do better than that. So what I do is, there are two ways we can represent this problem in the form of a tree. One is that we make a yes no decision. So I am at the start node. I have not actually, let me just try to write a smaller so that I have more space to do the drawing. Okay, I start at my root node. My sum, so this is how I define my problem. My node will hold the sum of the, okay, let's not go there first. Let's say I have the root node. So that means I'm at the first point of my decision making, and I have the first element in front of me. I can either decide the first element can be in my solution or it might not be in my solution. So if it is in my solution and if it is not in my solution, then I get to these 2 points. Then I decide about my second. So my first element is, if I have taken picked up 2, my sum is 2. If I have not picked up 2, my sum is 0. Then if I pick up 4, if I leave 4, here again pick and leave. If I pick up 4, my sum is 6. If I don't pick up 4, my sum is 2. If I pick up 4, if I don't pick up, I get to this point. Okay. Then next is, if I pick up 6, I get 12. If I don't pick up, I'm at 6. Pick up 6, I get at 8. I don't pick up 6, I'm still at 2. Pick up 6, I get 10. I don't pick up 6, I get 4. Pick up 6, I get 6. Don't pick up, I get 0. Okay, so let's for now just eliminate this 9. It'll just make the tree very big. Okay, now 1. Just write 1 will give me 13 and 12. Will give me 7 and 6. Will give me 9 and 8. 3 and 2. 11 and 10. 5 and 4. 7 and 6. 1 and 0. And the next one is 5. So 18 and 13. I'll not write numbers. That's not going to give me the solution. So this is just the leaf node. This will again not give me the solution. Here 5 will give me 6 and 1. This will be 5 and 0. So let's say 9 is not there. So you have some values here as well. They're not the solution values, so I'm not writing that. 8 got there. Okay, 4 and 2. Okay, yes, here 4 and 2. So here 6 and 5 is 11, and 6 and not taking 5 is 6. So this is one leaf that has the solution. This is another leaf that has the solution, and this one also. Here this will be 11 and this one will be 6. So there are 3 leaf nodes that give me the solution. Rest all these will not have values which can classify as the solution. So if you look at it, at every level I am taking, here I have 0 items. Here I take first item or the first element, and I decide whether to take it or to leave it. Then I after deciding, I have two options. In that those two options, I decide whether to pick or leave the second item. Similarly, third and fourth, and this is fifth. When you decide to take five or not, I've just eliminated nine because I don't think I can draw beyond this. So if you follow the path that takes you to six, let's do this one path here. One, one, one. So one, one, zero, zero, zero. So the path one, one would mean pick up one and two element, which is two and four, and then rest all is zeros. That is giving you six. Here zero, 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 one, and six. So three zeros, and this is your left. This is one and one and one. So three zeros, one and one means you're picking up one and five, and this six is zero, zero, one, zero, zero. So I just write them down: one, one, zero, 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 one, one. These are the paths I'm taking: zero, zero, one, zero, zero. So this is your 2, 4, 6, 1, 5. So this is 1 plus 5, this is 2 plus 4, and this is 6 only. So in this case, when you make the tree like this, where every level you decide whether to keep something in your uh, solution path or leave something, we represent the solution in the form of this. This is one solution, which means you had five items, you picked up first two, you dropped the three. This is another solution, and this is another solution. So there are three solutions to the problem, and you represent the solution in the form of, we call them tuples. So if you see, the size of the tuple is same. It is equal to the number of elements in the set, initially five. Nine is not there. So the size of this tuple is 5. The solution set has fixed size tuples with ones or zeros, which tells you what the solution is. We call this tree that we create, it is known as a state space tree. So in a way, this is used a lot in AI and other things. You are actually projecting all the possible options that can be generated in the form of a tree. And then you are searching the tree for solutions. So if you are making, let's say, a robot, okay, you will give that robot a, let's say, with a state space tree like this. So this tree, or this is basically what all you can see can happen, but then based on intelligent decisions, we will see which path we will traverse. Okay, so if you have to look for a solution in this type of a tree where it's a fixed state space tree, you have to basically explore the leaf nodes to see which leaf node has the value 6 and which path you can take. But you don't necessarily need to explore the entire tree. Although we are making the entire tree, when you write a program, you know certain things about your problem that you will not need to explore all the trees. We'll come to that later. But for now, this is one way of representing your state space tree, in the sense, one way of projecting your possibilities in front of your program and then asking your program to search for a solution from this state space tree. This is called the fixed state space tree. Let's go back here first. Okay, so before going here, this is, yes. So this is another example of sum of subsets problem. You have three elements in the set, 2, 4, and 6. Sum is 6. So there are two possibilities. If you see, this is the yes no tree that we are making. It is called the state space tree. There are three items, so there will be four levels. So you do a yes no, and based on that, you create the sum, and then the sum you need is, so this is your solution and this is your solution. Okay. Somebody's mic is on. Now, this tree is there. You want to look for a solution. So you have to go, in this case, you have to go all the way down to the leaf to see if there is a solution, that is sum 6 that we are looking for. So when we do a depth first of this tree, how will we proceed? We'll go here. So 12 is a failure in the sense we do not get success. Come back and then go here. This is success. Okay, you go back again, a failure, no solution, traverse, no solution, no solution, solution. Okay, so we will create the state space tree and then search it using DFS. So here DFS makes more sense because your solutions are at the leaf. So if I try to do the same search using BFS, this is how I will proceed. Layer by layer. So I will reach the solution probably later than what how I will reach if I'm doing DFS, because my leaf nodes will be searched at the end. So this is one way of uh, projecting your possibilities in the form of a tree. So this is a fixed state space tree, or we call it a fixed tuple state space tree. Why fixed tuple? Because all our solutions are in the form of a tuple and they are fixed in size. Okay. Okay. Did not save. So this is my fixed state space tree. Now I can, there's another way of doing or representing my problem in the form of a tree. Just keep this here. So I start at, let's say, sum 0. At the first moment itself, I'm not looking at the items one by one. I am looking at what are the 5 possibilities. I can either start with picking up 2, or start with picking up 4, or start with picking up 6, or start with picking up 1, or start with picking up 5. So there in the previous one, I was picking up, deciding whether I should pick or drop 2. Then whether I should pick or drop 4 at both the uh, branches of the tree. Here I'm doing it in a slightly different way. Whether I pick 2. So if I pick 2, then I have, if I pick 2, have still 4 possibilities of picking up 4, 6, 1, and 5. If I pick 4, if I pick 4, that means I have gone beyond picking up 2. So I have kind of dropped the idea. So my first choice is picking up 4, and after 4, I can pick up 6, 1, and 5. If I have picked up, just a second. Okay, so uh, if you pick up 2, you have the option of picking up 4, 6, 1, 5 after that. If you pick up 4, that means you've skipped the option of picking up 2. Now you have option of picking up only 6, 1, 5. If you have picked 6, you have two options of picking 1 and 5. And if you have picked 1, you just left with the option of picking 5 after that. And if you picked 5, there's nothing left after that. So that is your only choice. Now, again, applying the same thing to the next level. I picked up 2 and I picked up 4. If I pick up 2, then I pick up 4. I'm left with 6, 1, and 5. If I pick up 2, I skip 4 and I pick up 6. So I'm left with 1 and 5. 1, I'm left with 5 and 5. Nothing, no option after that. So similarly, 4, 6, you are left with 1 and 5. And 1, you just left with 5. Here 1, 6, 1, and 5. Okay, so you see some are ending at earlier levels themselves. So again we come here after 6, you can have 1 and 5. 1 you can have 5 and you're done. Here 1 you can have 5. 1 you can have 5. That's it. So what I've drawn here is just the elements. I haven't actually put the sum. So now I'll put the sum next to each of the nodes. So if I'm here, sum is 2, 4, 6, 1, 5. If I'm here, sum is 6, 8, 3, and 7. It's 10, 5, 9. This is 7, 11. This is 6. Here it is question. One more 5. Okay, yes, one more 5. Okay, I just go there and then draw it. So 6 plus 6 is 12. 1, 2, 12. 6 plus 1, 7. 11. 8 and 1, 9. 8 and 5, 13. 3 and 5 is 8. 10 and 1 is 11. 15. 10. This is 12. And then this is 13, 17, 12, 14, 16, and there is one more here. There's one more 5 here, so the sum will be 18. So if you see, this 18 is the sum of all the elements. So what we are looking for, our goal is the sum 6. And where do I have it? One is here. Another is and another is. So basically, now in this type of tree, when you actually hit a goal, you don't need to go beyond that. So if you look here, I already reached the goal. So adding anything to my goal after that is not going to give me the solution of, obviously. So there is no point in going beyond that. So I could have pretty much stopped here where the blue line is. So we call that, I could have pruned my tree, in the sense, when I actually come looking, this is the actual tree that is there. But when I actually come to search, let's say I apply depth first search. So I come here, then I come here, I reach here. So I see my goal value 6 is there. So I don't, obviously adding something else beyond it, it's not going to give me the solution. So I kind of restrict my tree till here. Okay, so this is one way in which you basically cut out the branches of your tree, so that your the density of the tree kind of gets reduced, so the area you have to search gets reduced as well. We call it pruning the tree. And how we prune the tree is by looking for basically using our intelligence to prune the tree. We know if we have found the solution 6, we know if you're going beyond, you're trying to add more to 6, so that's not going to give you a solution. That is one way of pruning. Another is here. So for now, these are the three goals that I have received. Another is, if I come here, okay, at this stage with that I marked or orange, my sum is 8. What I'm looking for is a sum 6. So I've already gotten 8. I was at 2. I was hoping from 2 to this I might get 6, but I have jumped to 8. So now, obviously, if I jump beyond 8, I'm going to get something which is above 8. I have already exceeded my target, which was 6. So I essentially don't even need to expand my tree where I have marked orange beyond this point. Okay, one is when I find the goal, I don't need to go beyond. Another is when I know that I have hit something which is not promising, in the sense it's already 8, it's not promising me a value of 6 after that. So I am not going to even expand the tree there. Here, this 3, this 3 here, it is still promising. 3 can give me 6, right? 3 is less than 6. I can add something to 3, it can give me 6. It is not giving me 6. That is another story, but I can, this one I can explore. Okay, then similarly 7, it's not going to give me the solution. So what I do is, we usually you'll see trees with a cross. So that is where we prune the trees or cut the tree branches, so that we don't search beyond that. So we have to search within what can or likely give us a solution. So when you go in the next one, uh, you see here, we can stop here, we can stop, it's already the last node in the sequence. And this one is still promising. Here, when you come here, it becomes 10. So again, here we can stop here itself, because we have reached the goal. And this one, so we have three, again we have three goal nodes here. Now if you want to represent them in the form of the tuples, okay, so you'll see the solution is, if you try to traverse the tree. So if you look at this branch here, make it some color. Yeah, if you go from 0 to 2, so 1, 2 to 4, 1. Okay, if let's say we go beyond, 4 to 6 means 1, 6 to 1 means 1, and 1 to 5 means 1. Okay, if you go from here 2 to 4 here, and then 4 to 1, so you're actually saying pick up 2, pick up 4, skip 6 and go to 1. So 0 and 1. So there is no actually 0 there, because there's no branch that goes to 0. So it's actually 1 1 1 1. So we don't, in case of a uh, we have a solution which is 2 and 4 based on the values. We have a solution which is 6, and we have a solution which is 1 and 5. So our solutions in the form of uh, in the representation, we do not have a uniform solution uh, in the form of a tuple. So the tuple size can vary depending on which branch you have taken and where you have pruned it. So this tree, that's why it's called either variable tuple state space tree or variable state space tree, because it's not uniform. If you look at the previous one, that was evenly branched it's like it that was like a binary tree. So you take yes or no, yes or no, yes or no at every level, at every node till you reach leaf nodes. All the leaf nodes are at the same level. Here you see all the leaf nodes are not at the same level. They are at all different levels. You have leaf node at level 1, you have another leaf node at level 2, at 3 also you have one, and so on, more than one, then 4, and then 5. So it is known as a variable state space tree. And the way we can bound or prune our trees in fixed and variable state space trees, it differs. Okay, in case of our variable state space, sorry, the fixed state space tree that I drew earlier, you can apply the same pruning. So when you see that a particular node sum is exceeding 6, so you can just cut off that branch. You don't have to keep it in the tree and make depth first search, go through that entire part and waste time. Because when you see, uh, let's say you are here, so you have 2 and you have, let's say, 8 and this 3. So this 8 is not promising, so anything below this, it could be a big tree here, you can just prune it off, you don't have to go there. 3 is promising, yes, let's go and explore what comes below it. Okay, so we kind of trim it off so that when we apply our depth first search, we are not wasting time in going in this area and doing nothing, because the solution is not going to be there. In this case, the way the problem is stated and the way the state space tree is created, the solution is not going to be below 8, because as you go down, you'll either be left with 8 or you will be left with 8 plus something. So this is you can just cut it off. If we come back here, so this what this slide talks about. Okay, there's a question: does this imply that these two algorithms can't manage negative values? Which two algorithms are you talking about? The state space trees I drew right now, they are based on the sum of subsets problem. The problem can differ. The state space tree will differ accordingly. The bounds that we apply will differ accordingly. Again, there are two different types of bounds that we have. We just talk about that. So it all depends on the problem. First, you see what your problem is. You create a state space tree. Then you think of ways in which you can prune the tree based on the available information or problem statement. And then once you prune the tree, then you can apply your DFS or BFS and then go about finding a goal or a solution in the tree. Okay, we'll come to that in a while. So this backtracking method that they're talking about here is the fixed state space tree. The root of the tree represents 0 choices. At every depth you take the first choice, take whether to take the first element or not, then you make a second choice and so on. Okay, uh, some terminologies before we may move ahead. Okay, I'll just read it out. I forgot to put some things in bold. So your problem state is each node in the depth first tree. So when you say I am at this node, you have actually come to a particular node, making a couple of choices and then getting to that point. So that is the state of your problem you are currently in. So if I have picked up 2, picked up 4, I am at that state. And then from there on, my decisions will further decide whether I'll get to a goal or not. State space is the set of all paths from root node to. So basically, state space tree is the tree of all the possibilities that are there. Solution states are the problem states for which the path from root to node defines a tuple in the solution space. So, like in the fixed state space tree, you have the solution states as you define the solution in the form of a tuple. In variable tuple size formulation trees, all nodes are solution states. So In case of the tree I just drew, which is the variable state space tree, the if you look back, if we go back here, your intermediate node here, here and here, they are the solution. So 5 is leaf, in this case this one is leaf, this one is not a leaf node, this one is not a leaf node. So any node can be a solution. But in case of the fixed tuple, you have to, the leaf node only can be a solution, because you're not yet you have to represent the solution in this form. So you have to know the entire path you took to get to the solution out of all the falls. Because of the nature of the state space tree, you have to, so all nodes will be in variable tuple state space tree. All nodes are solution states. Only in fixed tuple, you have only the leaf nodes. Okay. So in case of your fixed tuple, you are partitioned into disjoint sub-solution spaces at each internal node. Uh, so answer states are those states for which the path from root to, just forget about it, it's just the tuple, that state for which you can get from root to the leaf with that particular tuple values. Okay, just ignore the statement as well, implicit and explicit. We'll talk about static and dynamic bounds. This is a bit mathematical for now. We don't want to go there. Now, state space tree is the tree organization of the solution space. Static trees are ones for which tree organizations are independent of the problem instance being solved. So sometimes your tree will be defined by the problem, and sometimes it will be independent of the problem that is being solved. So I think next. Okay, what I want is you to know these few terms. Whenever we are at a space in a traversing a state space tree, if I am at a particular node and I have not yet explored the children of this node, so this is, you can imagine you standing at that node and deciding where to go from there. So this is your live node. So you are yet to know what the children nodes are and yet to go to any of these children nodes. So the node you are currently at exploring is your live node. Okay. Now they call something like a, known as a E node. So if when you have a live node and you generate its child nodes and you are either generating them or you are exploring them or they are being explored. So this is a E node in the sense that if I am at root node and I have, if I am backtracking, so this my root node will not turn black till all the nodes are explored, all the child nodes are explored, or they turn gray or black for that matter. So it is not the node I am currently on, but it is still alive because I will get back to it and then go to another child from there. Okay. And dead node is something that has either not been generated, no, sorry, which has been generated, but it's not to be expanded any further. That means something that we crossed out because it will not give me a solution. It is a dead node. So I'm not visiting that node. So either all the children of the dead node are already generated, or live nodes that are killed using a bounding function. Like I said, if the sum is 8, it's not going to give me anything. Obviously, it's going to give me more than 8 when I explore it. So I can just kill this node. So it will become a dead node. So, or it can have a value of 3 and all its children are explored and none of them, all are generated and we are exploring them. I don't, possibly there's no possibility of coming back to this node. So that can also be called a dead node. So this is the example. Mm, So now whatever state space tree you have, we can do a DFS on it. For some problems, we can do a BFS also, depending on the type of tree. When you have a fixed tuple state space tree, you have to go to the leaf node, and if you use DFS, then you will be able to go to the leaf nodes first. If you use BFS, you will explore level by level and you'll go to the leaf nodes at the last. So better is to use DFS for a fixed tuple state space tree. For a variable tuple, you can use a BFS also to find the solution. So you will see that we'll do problems where we'll apply all the approaches, BFS, DFS. And what will happen is the order in which you explore the nodes, that will be different. And the order or the time it takes to get to a solution, that will be affected. So since DFS, obviously it will be slow because it involves recursion. You are exploring every child one by one. So to improve our efficiency of uh, the search of the state space tree, what we do is we prune, like I said, we prune our trees. And how do we prune? We decide based on certain factors given in the problem statement whether a particular node is, we call it whether it's promising or non-promising. Promising whether it can likely give us a solution, and in some cases it can likely, maybe we already got the solution, but it's likely that it'll give us a better solution in case of optimization problems. Then it is a promising node. If it's a non-promising node, there's no need to explore it any further, so you can just cut down the tree at that point, and you have a reduced state space tree. So if a node is promising, go and explore it. If it's non-promising, then backtrack to the parent and then continue from this. So, okay, let's go here. This is, you have four elements, 3, 4, 5, 6 in the sum of subsets problem, and your sum is 13. Okay, and they're making a fixed tuple state space tree. So 3, 4, 5. So okay, so if you see, there is a cross at 8 also in the here. Let me mark it. So ideally, 8 is a promising node in the sense that it can give you further 3, 4, 5, and 6. Yes, it can give you. I don't know how what bound they have applied here. Let's go back and see. Some of I don't know why what bound they have applied at 8. So 12. The sum is 13. Okay, just skip this. I don't know, but they have not explained. Okay, this is again back applying DFS on this node. Okay, so this is, we'll do another example to explain this bound pruning. So you have two types of bounds that you can apply on your problem. One is called a static bound. So static bound is something like for the sum of subsets problem, if you are looking for a sum of 6 and your node has a value of 7, and it can be explored further, but 7 obviously it's already exceeding your goal, so it is a static bound which will be same across your whole problem or across the whole time you are searching in your state space tree. It's not going to change. Static bound stays same throughout your problem, throughout your searching the state space tree. there is something known as a dynamic bound, which will be applicable only in some kind of problems and some types of trees. For example, if we are looking at our, let's go back here. Okay, just so if we look at this tree, there are so in this problem we had, uh, if we apply, let's say we apply depth first search, so we'll explore this node first here. So I'll get the solution 2 and 4. Then it'll go all the way, whatever pruning or not pruning, it'll come here and I'll get this solution. And then all the way when you reach here, you'll get this solution. If my problem says that I want that solution which has the least tuple size. So least tuple size means here my solution tuple size is 2. It's 1 and 2. So obviously this is the least and this is my best solution. So if I am traversing this tree in a BFS order, I will first encounter this solution. Then I will encounter this solution. So if you check these two solutions, earlier the tuple size was 2, now the tuple size is 1. So obviously you've got a better solution. What happened? Okay. So when I was performing my DFS and I encountered this. So that means here. This means that if I go any level down than 4, maybe not in the same branch as 4, maybe in this branch somewhere, maybe there's a solution there. But if I go down further from this level, my tuple size is going to increase. So when I am at level 1, I'm doing a DFS. So I'll go from 2, I'll reach here 4. Then this is my goal. Then I, let's say, come back at 6. And then from 6 I can go, or I am here at 1, from here I go to 5 or somewhere. And it's giving me a solution. But that solution size will be, the tuple size will be more. So if my problem states that the tuple size should be as less as possible, I have already found a solution with tuple size 2. If I go down, maybe I'll find a solution, but the tuple size will increase, which is not my requirement. So I will not go there. So I will apply a dynamic bound, as in when I've already found a solution with the tuple size of 2. Why would I go and find a solution with the tuple size of 3 when my problem says that your best solution is the one with the least tuple size? So there's no point in going there. So I will kind of, even I can skip all of these as well, because they are again going to give me a tuple size of 2. Maybe if my goal is to find only one solution, then I'll go back, come back here, and then I'll encounter this. So my tuple size is 1. So my uh, currently my bound was, I in when I start the problem, I can have, I don't know what tuple size will I have. I find a goal with tuple size of 2. So I make that my bound. Don't go anywhere which will give you a tuple size of 3. So I prune all the branches based on that. Then I go and explore. I find the 6. My tuple size is 1. I found a goal and its tuple size is 1. So now my dynamic bound changes to 1. In the sense, don't go to any solution, don't go to look for a solution anywhere if the tuple size is more than 1. So it will not even go and find this solution, because this means going one level down. Okay, so this means going one level down, increasing your tuple size. So it will kind of prune this as well. Okay, is this clear? All right. Now, in case of DFS, this is first I'll explore this, then I'll explore this, and I'll actually not go and explore this because it doesn't make sense. Now, if you apply a BFS to this, if you apply a BFS to this graph, you will first find, you'll first find this, right? You are going like this, level by level. You'll first find this goal node with a tuple size of 1. So now if you in BFS you go to the next level, you'll find two more solutions there, but the tuple size will be more than 1. So if you are searching with BFS, you will stop only at level 1. So your dynamic bound, in case of when you use depth first search, your dynamic bound was tuple size 2. It changed from tuple size 2 to tuple size 1. That was your dynamic bound. So dynamic bound will change as you search the state space. When you were doing BFS, your dynamic bound was set to 1 when you found the first goal, and it did not change to anything after that because this is the best solution you can have. So this dynamic bound will vary in the course of running your search on the state space tree. Okay, static bound will be same. So in this case, static bound is sum is 6. Any node giving you greater than 6, just cut it off. So that is uniform. It doesn't matter how you are searching DFS or BFS, or um, it's not dependent on how you're searching and where you're searching, when you're searching, time. It is independent. It is always the same. Static bound is if sum is greater than or equal to 6, you can stop there. Okay, and dynamic bound, in case of a fixed tuple state space tree, this will not be valid, this kind of a dynamic bound, because it doesn't make sense. You have a fixed tuple answer. But here, dynamic bound will change based on your way of searching also, and time of searching, when you searched for what. Okay. Okay, I think we'll start this with the next problem next time. Okay, all right, I think we'll stop here today. I just modify these few slides and then before I upload it. Okay, Aman, did you take the attendance?
Yes, mom.
All right. All right. Uh, I might not take class tomorrow. I am busy. I'll inform Aman late, maybe early morning tomorrow. Mostly, I won't be taking class. So if you want to schedule something else, you can do it.
Okay.
Okay. All right. Thank you.
Thank you, mom.